So welcome to the first lecture on the simple harmonic oscillator. So the simple harmonic oscillator is one of the most important problems in quantum mechanics. So this is so important that I'm going to dedicate 2 lectures on it. And I'm going to use 2 very different methods to solve the same problem. So the topic of today's lecture is and this will be the first lecture on this. So why is the simple harmonic oscillator so important? So the quantum version of the simple harmonic oscillator, the importance of it becomes more and more apparent as you get into higher level physics. But heuristically, this is the reason why the simple harmonic oscillator the simple harmonic oscillator crops up in all kinds of places. So suppose that you are trying to quantize some arbitrary system, that a system has a potential so that you're going to expect some sort of bound states. So the potential can be, say, of some form, so because it's going to be some kind of a bound state, we are going to assume that it'll have some minima. So it could be something like this, an arbitrary potential. But see that if we now look at the ground state of this system, the energy of the ground state will be somewhere around here. So if you look at small oscillations of the system, then we just have to zoom into this region around the potential. So in other words, if this point is, say, x0, we will expand the potential around that point. And if we expand the potential around that point, the minimum value of the potential is going to be Vx0. So that's going to be this point, this height. And then because it's a minimum, the linear term in the Taylor expansion of the potential around x0 will be absent. So the first correction will be x minus x0 whole squared, and then the second derivative of the potential at the point x equals to x0. So by a judicious change of variable, you can always add a constant to a potential. So if you subtract this constant from your potential and then introduce some new variables such that x minus x0, some new coordinate system, goes to x. In other words, you're choosing your coordinate system in such a way that the minimum of the potential appears at x equals to 0. Then your potential will look something like half a constant. So this half k is, should be a 1 over factorial 2 here. So this k is basically this constant. So this will be half times k squared, and then higher order terms, where k is a positive constant. So graphically, what is happening here is that you are approximating this region around the vacuum, around the ground state, as a parabola, a parabolic potential. So of course, we know that this is precisely the potential energy of a simple harmonic oscillator. So for example, so any small deviation of any system from its minimum or its equilibrium position will be approximated by the simple harmonic oscillator. That's why the simple harmonic oscillator is so that's why the simple harmonic oscillator crops up in all different places. So for example, for small oscillations, of atoms, we can approximate the oscillations by the simple harmonic oscillator. Of course, for large oscillations, so when oscillations are large, then the harmonic or the quadratic approximation to the potential breaks down. Then you'd have to deal with what is known as an anharmonic oscillator. But we shall not go into that in this course. Okay, so we're interested in the quantum simple harmonic oscillator. So that means that we want to start with the Hamiltonian. So what is the Hamiltonian? So the Hamiltonian of the simple harmonic oscillator is going to be given by the kinetic term, which of course is p squared by 2m, or half mv squared, and then half of kx squared. So this is our Hamiltonian. And so let's spend a minute on the classical solution. So we all know, what is the classical solution to the equation of motion. The classical solution to the equation of motion, and let me remind you what the equation of motion is. The equation of motion is going to be given by the force, which is minus kx, is equal to the mass times the acceleration. So this is the equation of motion, and if you integrate this once, you get the first integral of motion, which is the energy. So this is the classical solution of the equation of motion, is of course the simple harmonic oscillator, and of course it's a second order differential equation, so there'll be two integration constant, and one would be the amplitude, and then we have a cosine, or you can write it sine, times omega t. Omega is the angular frequency plus a phase phi, which determines the position and the velocity of the particle at t equals to 0. Then the total energy, of course, is going to be equal to the potential energy and the kinetic energy. And we know that the kinetic energy is going to be 0 when x is equal to a. So that's when the total energy would be equal to the potential energy. So we can use that simple fact to write down what the total energy of this system is going to be. It's going to be k, half of k, a squared. And of course, we can express that in terms of half of m omega squared a squared. Now, you have to verify that for this to be a solution to this equation, what you need is that you will need that the angular frequency is going to be equal to k, the spring constant, divided by the mass square root. So this is something you should verify if you have not seen this before. It's very easy to verify. All you do is that you plug that into this equation, and that you'll see that for this equation to hold, k and m will have its combination will be related to this. So quantum mechanically, the equation is going to be the Hamiltonian operator acting on psi is going to be E psi. So this is the time independent Schrodinger equation. So why are we solving the time-independent Schrodinger equation? Well, it's very simple, because if we find the energy eigenstates, we can find the time-dependent solution just by multiplying it with the appropriate energy-dependent phase factor. And also we are looking at a bound state or a system which is bounded. So we are interested in the energy eigenstates. So as we saw in a previous lecture, if you solve the time-independent Schrodinger equation, then you've essentially solved the problem. So this equation explicitly is going to be d squared psi dx squared plus 2m by h bar squared times e minus v, which is half kx squared times psi is equal to 0. Now, so this equation as it stands is a little cumbersome to work with because of the presence of all these constants. So we are going to introduce some new units or new variables so that the equation becomes a bit more streamlined. So we are going to measure energy in units of E0, which will be given by half h bar omega, and then the energy E is going to be lambda times half h bar omega. So lambda, we are going to be measuring energy in terms of lambda, which means we are going to measure energy in units of E0. And then, you know, the amplitude for an oscillator whose energy is half h bar omega is then given by A, and that's going to be h bar by m omega square root. So what we're going to do is that we're going to say, you know, our position, our amplitude, or our displacement of the oscillator will be given in terms of let's call this A0 times x prime. So if we do this, if we introduce all these guys, then our Schrodinger equation becomes m omega divided by h bar, and then we have d squared psi dx prime squared plus lambda minus x prime squared psi is equal to 0. So this is just a constant. This is a constant factor, so we can just like drop this. And also, you know, it'll be cumbersome to keep on repeating x prime everywhere, to put primes everywhere. So we are going to do, what we're going to do is that we're going to relabel x prime by x. So then our Schrodinger equation becomes d squared psi dx squared plus lambda minus x squared times psi, and that is going to be equal to 0. So so this is the rescaled, you know, kinetic term, and this is the rescaled potential energy term, and this is the rescaled energy term. And next we will see how this is solved, but just note that, you know, this equation has the form of some differential operator O acting on the wave function, giving me something which is the wave some eigenvalue times the same wave function. So this is actually it's an eigenvalue problem, as we can see.